So hello, everyone, and welcome again to Inspiration Exchange. First off, very happy new year to you all. Thank you very much for joining us for our first session of 2022. Today's session is on machine learning to transform organ transplantation. My name is Nick Maxfield. I'll be moderating today's session. The session will be led by Mihaela van der Schaar, and we'll also be featuring a number of both our lab members and some of our clinical collaborators, pretty much for the first time in this series. So first, to give you an idea of what to expect from today's session, as always, our ongoing aim with Inspiration Exchange is to share and explore the breadth of topics in machine learning for healthcare and to generate ideas for future research projects. Last time, we focused on how to make machine learning models as useful and robust as possible. We looked at a range of topics such as synthetic data, fairness of synthetic data, uncertainty, missing data imputation, and so forth. But this time, we're shifting gears a little bit, and we are looking at machine learning for organ transplantation. I expect this to be quite an impact-oriented session. We'll be featuring presentations from and discussions with a number of clinicians, which is something we haven't really done before. And we will also be showing a newly developed demonstrator for organ transplantation. So to break this session down for you time-wise, after my short introduction, Mihaela will give a few words of welcome. And then we will show a short presentation, kind of an overview on organ transplantation, the importance and complexity of this as an area, which will be given by Dr. Alexander Gimson, one of our clinical collaborators. And then we'll be kind of shifting on to some of the ML methods and approaches. Firstly, starting with the problem of matchmaking and queuing, which will be a presentation mainly given by Jeroen Berrevoets in terms of its methods. And then we'll have a presentation by Bogdan Cebere, who will be introducing our demonstrator related to this problem. Then we will look at the problem of transplant decision-making, basically understanding and improving transplant decision-making. And this is kind of a joint presentation given by Fergus Imrie and Yuchao Qin. And I'll introduce all of these shortly before we show each one of them. After this, we will head into a roughly 15-minute discussion with three of our clinical collaborators, Dr. Alexander Gimson, Dr. Brent Ershoff, and Dr. Vasilis Kosmoliapsis. Then we'll be finishing up with a short Q&A, an audience Q&A on the methods and presentations, and basically anything that you'll have seen in the session up to that point. So if you do want to post any questions for us to discuss, please put them into the Inspiration Exchange Slack channel. The earlier, the better. And if you don't know how to access the Slack channel, please just have a look at one of my previous emails about Inspiration Exchange, and you should find the link in any one of them. So please just follow that link. Now, before I hand over to Mihaela, I just wanted to point you towards a couple of recently produced resources covering some of our work on organ transplantation. The first of which is kind of a spotlight piece, which is like a high-level overview, which firstly introduces the problem of organ transplantation and fleshes out some of the particular areas such as prediction, matchmaking, and allocation policy, and also introduces some of our own lab's pioneering work in this area. And if you want to find that, all you need to do is go on our website, and it'll be under Impact. There's a little submenu, and it should say Organ Transplantation. And the other is actually a recent engagement session that was part of our Revolutionizing Healthcare series, which is aimed at clinicians. So we held this session on organ transplantation at the end of November last year. And it really takes more of a clinician's approach to this topic. We feature a few presentations as well as a roundtable featuring a panel of international clinicians, all of whom are transplantation experts, who discuss opportunities and future directions for machine learning tools for organ transplantation. If you want to find this, all you need to do is go on our website, and it's under engagement sessions on the Revolutionizing Healthcare page. You can also go on our YouTube channel, and it's in the Revolutionizing Healthcare playlist on that channel. So now I'd like to hand over to Mihaela, if possible. So she'll give a couple minutes kind of welcome, just overviewing some of our topics for the day. But if you want to ask her any questions, please do put them into the Slack chat. Mihaela, whenever you're ready, please go ahead and share your screen.
Thank you very much, Nick. First, I would like to wish everyone a very happy new year. Thank you so much for coming and joining us yet again today. I'm very excited about the session today because of many reasons. First, it's the first time that we invited a few colleagues and collaborators from the clinical side to join us and tell what they think about machine learning and the role it can play in healthcare. So it's an opportunity for us all to really interact with them, and I really invite you to engage with them. I'm also very excited because this topic of organ transplantation poses numerous challenges for machine learning. It's actually a very complex and complicated area for machine learning, as you are going to see. And I think there are tremendous opportunities for machine learners to contribute to this area. It's also a very interesting area because of the impact it has. Really, transplantation is a very complex discipline, as you are going to hear a little bit later from Alex. And in discussions with Brent and Vasilis, hopefully you are going to see other aspects. Without further ado, let us start to hear more about this.
Okay, thanks very much, Mihaela. I think we may have one or two people on unmute, so please, if you could mute yourself, that would be very helpful. Thanks very much. Okay. Right, so first up, we have a presentation, as I mentioned, by Dr. Alexander Gimson. This is a recorded presentation. It's about 7 minutes in total. If you do want to view a longer version of it, you can find that in the Revolutionizing Healthcare session that I mentioned just a couple of minutes ago. And if you do have any questions for Dr. Gimson, please post them into the Slack chat. He has kindly joined us today, so he will be able to take questions.
Hello, I'm Alex Gimson. I've been a transplant hepatologist in Cambridge, and I'm now working with Mihaela. We're discussing today artificial intelligence and organ transplantation. Why is this an important area? Well, clearly, throughout transplantation, in most transplant jurisdictions, there is a significant disparity between demand for organs and donor organ supply. We think one of the other reasons why this is an important area is because transplantation is a paradigm for the use of scarce healthcare resources. It doesn't matter whether you're talking about organs for transplantation or the use of a scarce resource such as intensive care beds during a pandemic. Some of the principles behind what we're going to be discussing today are entirely relevant to the allocation of any scarce healthcare resource. But why is this a complicated area? Firstly, there is a multidimensional donor and recipient space. There are numerous non-linear interactions and factors within that donor and recipient space. We have to consider counterfactuals, not just what are the outcomes with a transplant, but what are the outcomes if you don't have a transplant, and what are the outcomes for all the people who don't receive the organ in question. And then with the database, there is significant issues of assignment bias and informative censoring. So we've elected to consider two main areas. Firstly, optimal donor allocation. Can we use artificial intelligence to better allocate organs for transplantation? And secondly, to interrogate the area of offer acceptance rates. There's a significant clinical variation between clinicians and between transplant centers in the rate at which a donor organ is offered. And we're interested in whether artificial intelligence can understand some of the reasons why clinicians may on one side say yes, or on another side say no. So just to set the scene, how we allocate organs currently in the United Kingdom is through a national liver offering scheme started in March 2018. Organs are offered on the basis of your net transplant benefit, the difference between your survival with and your survival without a transplant. And we currently use a Cox proportional hazards models. 17 different donor and recipient factors went into the original model. There are interaction terms, and that methodology has significantly reduced our mortality on the transplant waiting list. But there are problems. It doesn't take account of nonlinear terms, it doesn't take account of counterfactual outcomes, and it doesn't take account of informative sensory. So if you were going to design an optimal organ allocation process, we think these are some of the factors you should be considering. First of all, what's the outcome without a donor? What is your predicted prognosis with the specific donor in front of you? How long you might have to wait until you got a better organ, or indeed the optimal organ for you, because the one in front of you may not be the best organ for you. And indeed, what would your mortality be whilst waiting for that better or more optimal donor? And of course, whilst you're waiting, new patients will come onto the list, and they may have a better outcome with the future organs than you do. So that will have an impact on your decision whether to take the organ or to wait for a better one. And indeed, whilst you are waiting, you may also significantly deteriorate. So your ability to survive a transplant may be significantly worse, particularly if you're having to wait significant periods for a relatively rare organ. So we've tried to consider all those different aspects, and we think answered some of them, which I'm going to describe now. So the first model we've described is OrganITE. This was presented at the NeurIPS conference last year, and this is a balanced score composed of transplant benefit using the standard AI methodology of individual treatment effects, as well as an estimation for each potential recipient of what their optimal donor might be, and the future probability of that donor arriving. How long will it take for you to receive your optimal donor, and what might the impact of that be? We have also developed that one stage further, looking not just at survival estimations by individual treatment effects and organ density, but also making the model interpretable, so you can interrogate why the model has identified one patient rather than another patient for the donor in question. And have used a new way of queuing theory to address the future organ availability. I'm going to, in the last few minutes, just address now the whole issue of what we refer to as quantitative epistemology. Can we identify drivers of clinical decisions at a population level in organ offer acceptance? That's been done previously using logistic regression, but we wanted to see whether we could, as a proof of concept, do the same using an artificial intelligence methodology of inverse learning. And then not just at a population level, but also at the level of a specific patient organ offering sequence, can we identify what were the drivers in specific decisions rather than at a population level? So all this work has been presented and worked on by various people in Mihaela's lab. One of the things that I've found most noticeable is that it's by presenting interesting and difficult queries to AI technologists, they have been able to come up with some really impressive techniques, which in turn can help us in the clinical community understand some of our decisions a little bit better.
Okay, so that was the short overview by Dr. Gimson, and we're very grateful to him for providing that to us. So next up, we have a live presentation by Jeroen Berrevoets, who is one of our PhD students. So he'll be covering OrganITE and OrganSync, both of which were briefly mentioned in Dr. Gimson's presentation a minute ago, and which were published at NeurIPS 2020 and ICML 2021, respectively. So Jeroen, whenever you're ready, please go ahead and share your screen. And if anyone has any questions, please feel free to post them into the Slack chat.
Okay, so thanks, Nick. Thanks, Alex, for the introduction. I'm going to discuss the first two models that Alex presented in his introduction, being OrganITE and OrganSync. So basically, I'll be answering the question of what machine learning can do in terms of allocation policies. So later you'll see Yuchao and Fergus present their work on clinical variation. I'll take a different perspective, being what machine learning models how they can help in assigning an organ that arrives to a set of patients in need of this organ. So when Alex explained the problem to us, we were very excited because the problem is very difficult from a machine learning perspective, being that the set of in-need patients is always changing. People are added to the list, people die on the list, people are transplanted organs. So the patients from which we can choose, it's always changing over time. We need to balance multiple objectives, being the time, outcome, waste of organs, etc. So it's not just the one objective. The treatment, being the organ, is unique, it's high dimensional, which is from a causality point of view, very difficult and interesting. And above all, we have a huge amount of impact when we actually improve these policies. So the policies I'll present are called OrganITE and OrganSync, where OrganITE will be doing some treatment effect estimation using balancing representations, optimal donors, so how we define those, and organ rarity. Whereas with OrganSync, I'll be combining survival analysis, synthetic control, and queuing theory. So the general problem, as explained by Alex, we can mathematize, if you will. So we have a set of patients, which we denote X, with a bunch of features like weight or age or some clinical features. We have a set of possible organs, which we denote O. Similarly there, so we have a donor weight, a donor gender, all that sort of thing. And we have an outcome given some pair. So when we pair an organ with a patient, meaning O and X, we observe an outcome, or we don't observe an outcome. So we also have a censoring indicator. So how these data are collected, you should imagine some sort of timeline. First, we start off with a set of patients in need. We denote this set XT. We then, if there is a new patient arriving, we add this patient to the set, and the set changes from XT to XT plus 1, meaning that at 2 different time points, these 2 sets are now different. When an organ arrives, we choose one patient from the set using a policy pi. So pi is a function that takes into account the set, the arriving organ, and it outputs a patient from the set. We then pair these 2 organs together, and at some point in time, some future point, we observe the actual life years that the patient lived with this organ. Maybe they die very soon, maybe they die at some later point. It's unknown directly after allocation. So with this notation, we can come up with a data set. And this data set contains a bunch of mathematical objects, X, O, Y, and delta being the censoring indicator. And we have some index per object, and we observe n of these objects. So with this data set, we want to create a new policy. The difficulty is, however, is that these combinations of X and O are completely determined by some past policy, like Alex indicated. This is what we call assignment bias. We actually have no idea what the outcome would be if we would have allocated the observing organ to some other X. We don't know what the outcome would be. So any ML-driven policy should take this into account when predicting transplantation outcomes. We need a way to correct for this. With OrganITE, we recognize that there is more than only outcome prediction, right? So we don't want to just select the patient who would yield our predicted maximum outcome. We want to take some other stuff into account as well. In particular, we take 3 estimates into account. The first one being how well the patient matches with the available organ. So that is the green part of this slide. How much net gain we may expect after transplantation. So, for example, gain in months, being with transplantation minus the survival without transplantation, and how rare the patient's optimal organ is in red. So in this case, in this setting, we have a bunch of patients. We have 2 purple ones, 2 blue ones. And according to these policies, this organ would be assigned to either the purple patient. This would be incremental survival or best match. And as you can see, the gain is highest and the match therefore also. So these 2 policies would assign this organ to this patient. None of the policies would assign it to this blue patient, which is kind of strange because this patient has very little time to live and the organ is actually quite okay. So by balancing these objectives, OrganITE finds that this would be the best patient to give the organ to. If, for example, the patient had to wait for the best match, it would have to wait a pretty long time because this blue organ isn't arriving until some time. So there are two main components in how to do this. So first is predicting the effect, for which we use a high-dimensional individual treatment effects model. And the individual treatment effects model looks a bit like this. So this is a neural net with a padded income, being we concatenate X, the patient features, to O, the organ features. We learn a representation using this padded income. And from this representation, we learn the outcome, which is learned through this mean squared error loss between observed outcome and then estimated outcome. And then a second output head, which will predict the organ type from a cluster. So we first learn a k-means cluster unsupervised. And in the case of OrganITE, we use 15 cluster centers. And we try to predict what organ cluster this pair would result into. We have this minus sign here, which makes this term act as a regularizer, which in reality, in our model, we actually model through a gradient reversal layer here. So what this thing will do is it will actually balance the representation of these organ pairs in such a way that we're not able to predict what organ originally was matched with this patient here. And doing so, we hope to achieve that this estimate actually becomes unbiased because we take into account the relevant features to predict Y, but not how to predict the cluster itself. Using this estimator, we then maximize over this objective, which is the weighted estimate with some function lambda. The function lambda is a combination between how the optimal organ of a patient matches with the actually observed organ and the rarity of the patient's optimal organ. With this, if the patient is in need of a very rare organ, then this weight will be very high. If the match, or if the distance between the optimal organ and the actual observed organ for this patient is very little, the weight will also be very high. So in this way, we sort of balance the ITE estimate of the organ onto X. ITE is then defined as the expectation of the difference between these two potential outcomes, where the one potential outcome is the survival time given the observed organ minus the survival time without the organ in question. This will always be constant. This one will change given a new organ. So this is what Alex termed as the net benefit of an organ in a patient. If we score each patient on the wait list using this function, then the top scoring patient will get the organ according to OrganITE. A second model is OrganSync. So with this, we try to solve the exact same problem as we did with OrganITE, but with a different approach. So first, we need some interpretability in these models. With our balancing representations, we actually create some feature set that we have no idea of how to interpret it. Also, if we learn OrganITE multiple times, the feature set will always look different in this balancing representation. Also, we want a more principled queuing theoretic framework. Right now with the ranking, whenever a new organ arrives, the ranking will look completely different. So we have no way of saying to a patient, yes, we'll estimate you'll have to wait 3 months, say, until you receive an organ. This is impossible with OrganITE because it is completely dependent on the organ arriving, which is random. Plus, we also want to handle censoring. So note that in our dataset definition, we had this indicator delta, which we actually don't use in OrganITE. For this, we combine synthetic control, which is a method known in economics, waiting time estimates, and survival analysis. So OrganSync works in 5 steps. The first and second step look like this. So first, we build a non-linear representation of the organ and patient pair, which we call U, in such a way that U is actually, from U, we can build a linear estimate of the outcome. The second step is we look for a vector A, which minimizes this function. In simple terms, A is basically a linear combination of all other patients all patients except the one we're interested in. So if we have the patient organ pair XO here, we want to rebuild this in the nonlinear space using a factor A. Factor A is then a sparse factor because of this first norm term here. What this will do is it will create a synthetic patient with a different organ O, for example, or in the case of OrganSync, the outcome without an organ. Step 3 is then let's build a survival model. And this survival model in particular is called the Kaplan-Meier model, where we model basically the probability of dying at some time point t versus, so the amount of deaths over the amount of people still alive at time point t. We only look for this in the set of patients which have a higher than some threshold in A. Using the survival model and the expected survival, we can place the patient on one of the following queues. So these queues represent a priority queue for each organ type, which is again learned using some clustering method. If the patient has a very long survival estimate, we can put them probably on the queue that is most fit for the patient, being the queue which would yield the highest survival time given the organ type here. If, on the other hand, the patient has a very low expected survival, maybe we should place them on another queue depending on what the estimated waiting time is on this queue. Using queuing theory, we can then estimate for each queue type what the expected waiting time will be for this organ type. So by balancing or by comparing the expected survival with the estimated waiting time, we can choose a queue from the set of queues K. Whenever an organ arrives, we check what queue the organ should go to, and then we just pick the top patient here. Having this model, I mean, it looks a bit complicated, but it has several advantages. First, having this linear factor A, we can actually query the model to see what past cases the model has looked at when making an outcome estimate, for one. And second, having queuing theory allows us to present the patient with a queuing or a waiting time estimate using queuing theory. So these are the two things we wanted to solve with OrganSync. So I'm going to present or finish off with some results of these models. The first one being prediction. So having OrganITE here and OrganSync, it yields way better predictions than any other actually in-use models we compare with. So Confident Match is a past paper of our lab. Transplant Benefit is currently in use in the UK. And Multitask is a naive benchmark using multitask learning for multiple organ types. So yeah, having the real factual data we see, we perform much better. And also in counterfactual, so with simulated data, we also perform much better using OrganSync with synthetic control, OrganSync without synthetic control. I mean, those results look pretty good, but this is where the actual meat is at. Like, we compare using a simulation, of course, what the amount of deaths and amount of, or the absolute, average life years gained using these models would be if we would actually implement them in practice. And we see huge improvements in comparison to other in-use policies. So FIFO is a naive first in, first out, but MELD and A, Transplant Benefit, and Confident Match are actually models that people could use in transplantation. And then a final result is what the interpretation looks like for OrganSync. So with this factor A, we built a synthetic patient, if you recall, and for this patient here, this is what their synthetic patient will look like. The first one has a 0.4, let's say like 40% of its estimates based on this patient. This is actually quite interesting because this patient doesn't look anything like this patient. So this suggests to me that there is some nonlinear stuff going on in how the outcome actually models in reality. And these are, by the way, the covariates that MELD and A uses to make their allocation predictions. Finally, I want to close with basically an introduction to Bogdan's next presentation, which is we built this thing called OrganBoard, which allows access to people to our models, basically. So allows access for people to our models, in this case, OrganITE. So you can play around with these covariates for patient and donor and see what OrganITE predicts for this patient and compare it with what the other models would predict for yourself. What's next? We are actively working with clinicians. Two of those are currently in this call to basically change policy. Like, we want our models to be used to allocate organs. This takes a lot more research and a lot more clinical validation, and people like Dr. Alex Gimson and Dr. Ben Ershoff are helping us to do this. And from a technical point of view, we're considering more formal queuing theory. Currently in OrganSync, we use Little's Law, which is a very standard queuing theory method. We want to do more formal queuing. Also, the policies I presented, they combine a bunch of different specific components, and research in these components, I think, is also a good way to move forward. And then a third component is evaluate basically how we should simulate environments in order to evaluate these policies more accurately before actually deploying them. So this basically combines a little bit into what we want to do on the clinical side, is think of good ways to evaluate and clinically validate these policies before use. That's it on my part. Thank you very much for listening.
Okay, and Bogdan, whenever you're ready, if you just want to share your screen. In the meantime, if anyone does have any questions for Jeroen, please put them into the Slack chat on OrganITE or OrganSync.
Thanks. Hello. I will talk about OrganBoard, the demonstrator we built on top of OrganITE, and the process behind it. Mainly, our goal was to create an app that displays the prediction methods of OrganITE. And the first step around deploying such a tool is about the stability. We want to have some reliable core components. But the most of the research code nowadays is written in Python, and it's not an ideal programming language for safe and reliable code. However, several open source tools can help us minimize the error window. And there are several good static checkers that are recommended in any Python project. As well, unit testing is recommended, and it's very good to have a good test coverage. This is not necessarily related to machine learning testing, but software in general, especially in Python, which is not compiled. And one of the most important advantages of open source community is the GitHub workflows feature. For every public repository, GitHub allocates free hardware for running tests on a custom test metrics for various configurations and on different operating systems. This allows us to have automated testing on all the configuration we want to support and prevent deployment issues. It doesn't exclude all the bugs, but it gets us closer to a reliable library using only open source tools. The second step is about benchmarking. We wanted to be able to compare our methods with established models and be transparent about the results. We added the well-known MELT, UCALD, and Cox models to our inference. They all have open source documentation, and we only needed to be careful about the scales and units for the features, which may differ from one model to another. The next step was about accessibility. We wrapped the library in a HTTP server with a well-defined API. API validation schema is constructed around the training set, UKREG in our setup, to prevent undefined behavior from any model. At this stage, the inference server could be queried with payloads like the one on the left, basically encoding a patient and a donor. And on the right, there's a JSON response with the scores from all the models we included from MELT to OrganITE. But the models behind OrganITE offered us the opportunity to extend the output of the inference server. One direction was to compute the mortality risk probabilities over a period of time with or without a transplant. This report may be informative than a simple score, and it was straightforward to acquire this information by adding a nonlinear survival model on top of the internal representation of OrganITE. And we are not covering the allocation policy in this tool. We are able to use the clustering models inside OrganITE for displaying donor availability probabilities as well. Finally, we added a simple user face on top of the inference server using Python dash. The AI server queries the inference server on every user input, and it's straightforward to scale these components in a cloud environment. And now I'll show a short demo of the tool. So you can see on the left, you have the patient input, and in the middle, the donor input. As you can see, we replicated testing scenarios from other tools like Transplant Benefit, just to validate our implementation. On the right, you can see the output of the survival function we talked about. Depicts the mortality risk probabilities over a 5 years time span. And next, you can compare with the scores from other models. In the middle, we also have the donors predictions, as I mentioned, and the probabilities of finding a similar donor to the one selected or the optimal donor. Thank you for listening. That's all.
Thanks very much, Bogdan. Okay, brilliant. All right, so our final presentation from our lab members is on one of the topics that Dr. Gimson mentioned, which is basically transplant decision-making or allocation policy. So this is a sort of a joint presentation by Fergus Imrie, who's one of our postdocs, and Yuchao Qin, who's one of our PhD students. It's about 9 minutes. The work that you'll see was published at NeurIPS 2021. Again, if you have any questions for either Fergus or Yuchao, please post them into the Slack chat.
Hello, my name is Fergus Imrie, and I'm a postdoc in the Schaar Lab based at the University of California, Los Angeles. I'm very excited to be speaking at today's Inspiration Exchange about our recent work on understanding clinical decision-making presented at NeurIPS 2021 that has a focus on organ transplantation. So why organ transplantation? First is that patients have heterogeneous responses to organs, and all organs are unique, making allocations and acceptance decisions highly complex. Second, clinicians' decision-making is poorly understood. Despite the allocation process being based on agreed criteria decided by domain experts and doctors, an organ offered to the first-ranked patient in the waitlist could be rejected up to 50% of the time, and many good quality organs are turned down several times before they're finally accepted. Understanding the reasons why doctors and patients accept or reject these organ offers could have a significant impact on organ transplantation, including at the allocation step. Finally, we wish to understand why decisions vary between doctors or transplant centers. Variation in practice is a well-established medical phenomenon that is not well understood, nor is it warranted, with a number of studies showing that variation in practice leads to worse patient outcomes. However, so far, it's been impossible to disambiguate the causes of this variation, despite its importance for understanding current medical practice and ultimately improving organ allocation policies and improving patient outcomes. Before proceeding any further, I want to emphasize that the goal of our work is not an attempt to replace humans, but rather to augment existing human decision-making and assist highly skilled clinicians in making challenging decisions. In addition, decisions on organ offers are normally highly time-sensitive decisions that don't allow for an extensive discussion among clinicians, making clinical support systems even more important in this context. In our paper, we propose an inverse decision-making approach to improve decision support tools by understanding current medical practice. We believe that decision support systems should have a set of desired properties, and in particular should be able to adapt to best practices based on past decision history, rather than relying exclusively on handcrafted decision rules. They should also be able to issue bespoke suggestions to doctors based on specific characteristics of the patient at hand. And finally, they should help doctors to reduce unwarranted variation in clinical practice and ultimately improve patient care. To achieve these aims, there is a set of key desiderata that inverse decision-making approaches must meet. In particular, they must be highly predictive of observed expert behavior and be able to learn individual policies. In addition, they should be interpretable such that they provide insight into the decision-making process. And finally, they must give consistent interpretations under perturbation so that we can ask what-if style questions and also be confident in the interpretations being proposed by the inverse decision-making systems. With these desiderata in mind, we formalize the problem as an expert policy learning problem from batch data with the objective shown on the slide. Due to time constraints, unfortunately, there's no time to go into this in more detail, but if you would like more detail, please see our paper. With that, I'd like to pass over to Yuchao to describe our proposed method and present our results.
My name is Yuchao Qin, and I'm a PhD student in the Schaar Lab based in the University of Cambridge. Following the introduction from Fergus, I will briefly go over our proposed method of iTransplant and introduce the associated experiments. As shown in this slide, there are two major steps in our proposed iTransplant framework. In the first step, patient covariates are mapped to a latent space with an encoder network. The autoencoder structure enables our model to capture the specific features of individual patients that are relevant to various decision patterns observed in the dataset. These latent embeddings are then used to identify human interpretable policies from the transparent policy space pi in the second step. The specific design of our framework makes sure that the learned insights are human interpretable and innately individualized for patients from different cohorts. To validate the four desiderata proposed earlier, we firstly conducted a benchmark with real-world liver transplantation data from the United States. The dataset covers organ offer records from 2003 to 2020, and 10 transplant centers with sufficient numbers of accepted organs are selected in the experiment. The result in Table 2 shows that iTransplant significantly outperforms all the baselines or white box models and feature importance-based models. More importantly, with the individualized policies, our method can achieve comparable action matching performance to black box models like behavioral cloning, while being much more interpretable. In the meantime, although black box models can be highly predictive of human decisions, they have to rely on post-hoc interpretation methods like LAMP to provide human understandable insights. As shown in Table 3, these post-hoc insights are usually highly inconsistent under moderate perturbations to patient covariates or donor organ off features, which further demonstrates the advantage of our method. In addition to the benchmark, we conducted 3 experiments to illustrate how our method can be used to investigate clinicians' decisions. Firstly, as shown in the figure to the right, iTransplant is able to discover the most significant decision drivers at the population level. This allows clinicians' decisions to be compared with clinical guidelines and makes it possible for decision support tools to highlight potentially overlooked factors to clinicians. Then let's take a look at the individual level. Our experiment shows that iTransplant is able to identify patient-specific organ preferences of clinicians. This enables us to examine the impact of organ features on the decisions made to the different subgroups of patients. Finally, we show that iTransplant could be used as a tool to discover mismatches in decision policies across transplant centers or hospitals. And this allows clinicians to explore and reduce variation of patient outcomes at the individual level. In summary, we highlight in this work that inverse decision-making approaches are the key to achieve flexible, closed-loop decision support with adaptation to clinical practice, and to help reduce subjective biases and unwanted variations in patient outcomes. It is worth noting that policies learned by most inverse decision-making approaches are just hypotheses. Human audits are always necessary when these methods are applied in reality, especially for medicine and healthcare. Also, the impact from the organ allocation system is not fully addressed in our framework, since we only focus on decisions that happened after the organ allocation. And we leave it for future work. If you are interested in the topic of inverse decision-making and its broader impacts, you're welcome to check our other works on understanding human decision-making.
Okay, brilliant. So now it's time for our discussion with some of our clinical collaborators. So I don't think we actually do have Brent Ershoff with us today, but we do have Dr. Alexander Gimson, who's a transplant hepatologist at Cambridge, who works closely with our lab. And we have Dr. Vasilis Kosmoliapsis, who's an abdominal transplant and hepatopancreatobiliary surgeon with the University of Cambridge and the NHS. So I think the way this will work is basically Mihaela will kick things off with a couple of questions for our two clinicians, and then we'll just have a sort of a broad discussion around these and any of her follow-up questions as well.
So thank you very much, Alex and Vasilis, one more time for being with us today. My first question is for Vasilis, since he was not involved in this research with us. Vasilis, why are you excited about machine learning? And are you excited about machine learning? And where in transplantation and more generally in medicine, you think that there are opportunities for machine learning to contribute to support you in your decision-making process or in any other way?
Thank you very much, Mihaela. I've really enjoyed the session. I mean, the work you've done with Alex makes the point perfectly. We've been using standard statistics to, for example, in organ allocation for far too long. The field is very complex. Relying on just modeling one outcome is really very oversimplified. And the work you just presented makes the point that using machine learning can help allocation and decision making. So that's one thing. I can think of, you asked what else one might do. I think the opportunities are endless, really. The liver organ allocation is a very good case to study, but you can make similar arguments at the organ allocation level for other organs, in particular kidneys. You can look at outcomes that are more nuanced. So survival is one thing, but the impact of having a transplant on a patient can be addressed in multiple levels. It's not just survival that matters. So one can look at a variety of outcomes to study. And it's complex because it depends on many factors. So typically in an organ allocation policy, we have a one-size-fits-all approach, which is not right. And this is reflected on how clinicians then make decisions. So for example, if I just bring an example of a kidney patient on the waiting list, the way you decide whether you accept an organ for a young patient versus an older patient is a completely different process. Similar considerations apply to what organs you accept. and also what outcomes you focus on. We focused on organ survival or graft survival, which is rightly so, but there are many other considerations. So one of the things I have in mind, as you know, Mihaela, is the sensitization aspect of receiving an organ transplant, how that affects immunosuppression decisions, the impact of immunosuppression on patient outcomes, and so on. I can go on forever. So yes, it's really very exciting, and clearly, in my view, without understanding the machine learning, the maths of it, very exciting.
Thank you very much. Alex, I'm turning now to you. You have been embarking in this research agenda with us for some time.
Yeah.
So what else do you think is next, and what problems didn't we address and you think are at the forefront of what you think is needed to happen to really change the way transplantation is done?
So I think some of what I'm going to say, I mean, Vasilis has already mentioned. I mean, the machine learning tools are fantastically powerful at bringing together a whole range of data, which we have not previously been able to do in our prognostic models. So one thing which would be close to what we've heard already is, in the past, most allocation processes have been based on patient survival. But it would be more logical to look at whether machine learning can improve allocation if you just considered organ survival, so that one can avoid, certainly in liver transplantation, up to 10% of all transplantation is currently a second transplant. If we could allocate better and avoid that 10% needing a second transplant, then that would be a significant advance. That would be one possibility. Secondly, I think there are, you have educated me about new machine learning methodologies looking at temporal phenotyping, trying to identify the clinical course of an organ and a donor pair. And we may be able to describe different clinical courses. And if we can describe different clinical courses, as Vasilis says, that may give us information about their risks of rejection, their risks of sepsis and infections, their risks of vascular complications. All these things may be able to be interrogated and predicted better by using different machine learning methodologies. And of course, if you can predict the future better, then you can allocate different organ recipient pairs to different monitoring policies. Some people may need more monitoring closer so that we can identify when a complication is going to occur earlier, and some people may need less frequent monitoring. And so I think the whole area of how we monitor our patients post-operatively could be informed enormously by identifying these different phenotypes of the donor-recipient pair.
Thank you. So I guess I have another question, maybe a final question, but a complicated one potentially. What would be your thoughts, to both of you, that what do you think is needed to get machine learning to be truly get all the way to implementation, such that it's really used by you and your colleagues? What do you think that we need to do as a machine learning community to make these tools ready, and afterwards, what is needed for their certification or for making them useful and usable?
Well, shall I have a go to start there? I mean, this is a really, really big question, and I think there are sort of at least two components to it. One is, in order to introduce machine learning technologies, there will be certain regulatory requirements. And I think at the moment, those regulatory requirements possibly have not quite kept pace with some of the new developments in machine learning. So I do think that transplant communities and the wider healthcare communities will need to think very carefully about how we are going to introduce machine learning and methodologies, both at an ethical, at a legal, as well as at a practical level. So the regulation of how we introduce these, I think will need to change. That's going to be the first thing. If you're looking at organ allocation methodologies, implementing those, of course, when these have been, new policies have been introduced in the past, it's noticeable that they have not been exposed to randomized controlled trials. People have done simulations, and if the simulation gave a positive outcome, then following debate and acceptance within the clinical community, they've been introduced. Maybe that's not quite the right way for the future. I think it would be interesting to do randomized trials of these policies, different units using different allocation policies to see the outcome. And maybe it would be a neat way if one could use, of course, machine learning and the new adaptive clinical trials processes to allocate allocation by different processes in order to optimize a clinical trial. So I think it will eventually come down, my personal view is, to clinical trials as opposed to just straightforward simulation.
Vasilis, what are your thoughts?
Well, I certainly agree with what Alex has said. It's very complex. It depends what you're trying to achieve. I guess allocation is a good example. It would be wonderful if we can end up testing allocation policies with trials. I fear that the subjective nature of transplantation would be an issue here. One of the problems in transplantation these days is that it is very successful as it is. So you really can't sort of rely, if you're modeling outcomes like survival, you need many years to wait to see these outcomes, you know, if you're talking about an RCT. So I would argue that you need good surrogate endpoints that can be accessed early, that you can use then for trials. As long as you identify that, then an RCT becomes more possible. But that brings me to my next point, that I think an area where machine learning can be very important is enriching clinical trials. And for example, we talked about immunosuppression. I'll give you an example from the kidney literature. People have tried to use a bit less immunosuppression, to minimize immunosuppression after 6 months in kidneys. In 3, I think, clinical trials over the last few years, using all available knowledge to define low risk. So biopsies, no antibodies, perfect function, you name it. And the trials had to be stopped because the patients rejected quite quickly. So the question is, can we use machine learning to incorporate the variety of outcomes that, for example, determine the chance of an immune response to enrich clinical trials? And one can see similar examples in other areas within transplantation. You can do other things. You can look at, I remember your work on ICU patients, how you do decision-making. I mean, how you manage patients when they're in hospital can be an application where decision-making tools can be used for specific interventions. And then the timeframes are more manageable. At the end of the day, I think us clinicians understand, or if you like, can have access to these tools, then the enthusiasm will increase, and understanding how they can be used will bring more clinicians into it.
So the demonstrators, like Bogdan has shown,
Exactly.
hopefully are going to allow everyone to interact easier with these methods. So I think that's part of, of communicating what the tools can do and debugging at the same time. Am I correct? How do you think about the role of demonstrators, Vasilis, in this area?
Well, I think that's wonderful. I mean, there's no other way. If you start talking about maths and virtual space and multi-parametric modeling, you've lost everybody. It's inaccessible to simpletons like us, but at least talking about myself. So you need something that, a tool like the one you showed in the last presentation. And I imagine, it depends. Similar tools can be applied to decision making. So, if you have a nice model, then you bring it into clinical practice. And even by seeing what the machine learning model might suggest to a clinician may be useful, and you can then build a study around that to see how one can use it. But it has to be simple to use.
Sorry, I think, Mihaela, you might have got cut off a second ago when you tried to say something. So should we move on maybe to, I think you're on mute.
No, I just wanted to invite everyone, if they have any questions, to Alex and Vasilis to ask them now, because it's a unique opportunity. We got one question that's of a more technical nature, but maybe we can take that while everybody can.
Yeah, shall we perhaps take the slightly more technical question first and then see if we get any others in the meantime? And I believe that one is from Shinkai Zhou. Shinkai, if you are able, would you mind unmuting yourself and hopefully also just being on camera to ask your question as well? It's a very good question, very much worth taking if you'd like to unmute.
Yeah, sure. So my name is Shinkai. I'm a fourth-year PhD student at UCLA Biostatistics, and I really appreciate that you guys organize this. It's my second time here, and I thank all of today's presenters. So my question is, so all of the methods presented today were based on deep learning models, but while I appreciate the flexibility of these models, I think they lack uncertainty quantification compared to traditional statistical methods, like, for example, logistic regression or some Bayesian, their Bayesian version. So in certain applications, like in business applications, one may argue that you can just rely. All you need is prediction, accurate prediction, and you don't have to worry about uncertainty, because making a wrong decision, like recommending a wrong product to a customer, is okay. But in these applications like organ transplantation, can we really live without uncertainty quantification?
Thank you very much, Singha, for this very important question. So I completely agree with you that we need uncertainty quantification for this method. Let me answer in two ways. So first, deep learning methods nowadays do have uncertainty quantification. And I'm not talking here only about credible intervals and, let's say, Bayesian type credible intervals. I'm really talking about hardcore confidence intervals and hardcore methods that were developed in recent years by various people, inclusively ourselves, that marry ideas from statistics with ideas from machine learning to provide post hoc uncertainty quantification. So actually, if you look on our own lab website, you will see a section that's called Uncertainty Quantification and Trustworthiness, which really presents some of these methods that have been developed in the last couple of years by our lab, but there are others that are developing them as well. And indeed, this is where machine learning and statistics are joining forces, if you like, because we really develop these true coverage guarantees for these deep learning methods based on ideas from statistics, but which can be applied to deep learning methods like the ones presented here. So this is now possible. So it's a frontier, but it is now possible. Also, in the previous inspiration exchange, there was a discussion about one such methods. And it was even presented for the more complicated case of time series. So please take a look at that. Let me also say that to my surprise, and maybe Alex Gimson can comment, or Jeroen can comment a little bit on that. To my surprise, the benchmarks, the existing methods based on which current transplantations decisions are made, do not provide such confidence estimates. So actually, my answer is yes, we should have them. Current methods which are not based on machine learning do not present them to the clinicians. And number three, yes, there are methods that can provide true coverage guarantees for deep learning methods. This is cutting edge machine learning, but it's now possible. Thank you. Alex, would you like to say anything about this, about the need for uncertainty estimation and maybe why current methods don't have them?
First of all, you are entirely right. So most of the current predictive models that people are using for organ allocation do not, when they have very good predictive parameters, they're not very accurate models. There are a number of reasons for that. Why they're not used is because I think when making the actual decision, should I use this organ or should I not use this organ in the middle of the night, in my experience, the clinician, I don't think, will be swayed so much at the point of making the decision by uncertainty prediction. But I think why it is useful is, in the cold light of day, clinicians accepting machine learning methodology as better than another allocation process, which may have a lower or a greater prediction uncertainty. Of course, you have to remember that predicting outcomes before a transplant is always going to be inherently slightly inaccurate, because there are many factors which impact the outcome of that donor-recipient pair, which occur at the time of the transplant. Because the transplant hasn't actually happened, you can only use a certain limited amount of information before you actually do the surgery. So these models will not be the most accurate way of predicting the outcome, because the information that predicts outcome isn't available at the time. You have to make that difficult decision. It does, therefore, in my view, make it all the more important that we do use uncertainty predictions when comparing one allocation process with another one.
Mm-hmm. Yeah.
Thank you very much, Alex. And thank you, Vasilis, for contribution to this session and for engaging with us.
Okay.
Thank you for answering my question.
So I think that probably brings us to as much time as we can allow for this session. But just before I go, a couple of quick notes from me. So first up, we are recruiting, we're still recruiting and still accepting some applications for a handful of fully funded PhD positions that will start later this year. If you are interested, please just visit our website and just click on just click on join us, and then you'll be taken to a page with a very simple form. Please just fill out that form. And additionally, so we have decided on when our next session will be and what our topic will be. So we will be doing this again in exactly 1 month, same time. And our topic will be machine learning interpretability. So this is a topic that we have visited in the past, but this time we'll be revisiting this topic, but looking at some of the newest, the next frontiers for machine learning interpretability, since this is such a crucial area at the intersection of machine learning and healthcare. If you do want to rewatch today's session, we'll be putting it up on YouTube very soon, probably the first half of next week. In the meantime, if you're just looking for additional resources, something to watch, I would like to point you towards a couple things. So firstly, we have a series of 3 talks Mihaela gave at NeurIPS 2021 workshops. We also have a playlist with basically 10 quite high-level mini seminars that we gave on a variety of our lab's research projects as part of our open house, which was held in October. And we have a kind of array of new content on a variety of topics, ranging from self-supervised learning to synthetic data, and even some additional topics such as uncertainty, which just came up a minute ago. These are available basically if you just go to our homepage and you look under big ideas or news, or you just scroll down through our latest posts feeds, because they'll all be in there. In the meantime, if you do want to stay up to date with Inspiration Exchange, you can also just visit a dedicated page that we have for these sessions on our website. And if you do have any friends or colleagues that you think would be interested in these sessions, please just let them know. Obviously, we are trying to build a community, so word of mouth is very important and valuable in doing so. And just before I sign off, I'd like to thank everyone who's joined us today, not only those of you who are participants in the audience, but also, of course, to our lab members, and especially to the clinicians, Alex and Vasilis, who joined us today. Thank you so much for taking the time to be here. Very much appreciated. And to all of the rest of you, very much looking forward to our session in February on interpretable machine learning. Thanks so much for joining us, and see you next time.
Bye.
Bye for now.
Bye. Thank you.